Good morning. We are looking at section 16.2 today, a really important equation for us in thermodynamics called the Gibbs free energy equation. You can see it there. You're going to be focusing on delta G today, but first what we should do is relate this back to delta S for the universe, because like we have down there at the bottom in the notes is that we know that delta S for the universe always has to be increasing. So let's use that to help us derive what that tells us about delta G. As you can see, it says there that delta G must be negative to tell us that a reaction is spontaneous. Let's prove that. So I don't know that you need to copy all of this down, honestly. I think it's important that you get this equation, of course, and we'll use it in a few minutes. But just to show you where this develops, we're going to start by dividing through by negative t. Okay, so if you go through and divide by negative t to all of these, so that's a t right there, to all of these right here. What happens on this one here is the negative t's cancel each other out. Sorry, I can't get the pen to write that. There we go. And that leaves us with delta S. Okay, that delta S is the delta S of the system. Okay, so keep on going with this. Then now it becomes positive because of the negative t canceling out. And then this right here, we remember this from yesterday's notes, that delta H, negative delta H over T is defined as delta S for the surroundings. Okay, so we have delta S for the system, delta S for the surroundings, and we know that those two things add together to equal delta S for the universe. So what that tells us then is that delta S for the universe, which we know has to be positive, is equal to negative delta G over T. Now, T's in Kelvin, so technically that negative sign can only be attached to the negative delta G. So in order for delta S to be positive, delta G has to be negative so that the negative signs cancel each other out. I guess would be a better way to think of it. Let's leave that negative sign out in front. I don't like the way I just said that to you earlier. So in order for delta S of the universe to be positive, delta G has to be negative so that the two negative signs cancel out and leave us with a positive answer on both sides of the equation. Okay, so there's the proof of how this works. I wouldn't say that you need to commit this as a formula, memory or on a cheat sheet or whatever. I can't picture a time where this equation is used. What's important is that you know that this is always positive in order for a reaction to be spontaneous, and this is always negative in order for a reaction to be spontaneous. Technically, delta G has to be negative for a reaction to be spontaneous. Delta S of the universe is always increasing. Even in non-spontaneous circumstance, delta S of the universe is always increasing. Okay, so part of making this all work right, I don't know what the derivation for this is, but we're going to call this delta S. You're going to see that little, the superscript 0 that's there, which just tells us that we're at standard pressure. And I don't know, we're just going to say that that's what makes this equation work. So just not, once again, something that you don't necessarily need to know. Maybe put that little 0 there in your notes, but you don't need to necessarily write all that down because there's no time that you're going to be referring to that. Let's look at our two factors of our reactions. In thermodynamics, we have both the enthalpy and then also the entropy, and see how what that tells us about temperatures that can allow the Gibbs free energy equation to be negative value. Okay, so maybe we're kind of thinking about the turning point. I don't know if you want to put a negative sign in on this side for where delta G is. We need to make that happen. And on this part of it, we have an endothermic reaction, which tells us that we have a positive delta H, right? And then the entropy increases, so minus T times delta S, which is also a positive value, a positive S. I don't know if I really want to include the S and the H in there, but they're already there. But you get what I'm trying to say here? And you know what? I'm going to take them out of there. I'm just going to put positive signs in there. You guys can see the formula up above. You know that what's going in here is the H. What's going in here is the S, and what we're told is that it's an endothermic reaction, so delta S is positive. System increases in entropy, so delta S is positive, and we need this to come out to be negative. So how are we going to have these two terms, which both are positive? Remember, T is a positive value always. It's Kelvin temperature. It's, 0 or positive. The only way that this can possibly come out to give a negative answer is if this term is bigger than this term is smaller, right? That's how you end up with a negative answer when you subtract. So what that tells us is that this is going to occur when T is relatively large. I can't say that it's going to be large, but we can say that it's got to be large enough that it causes the delta S term to be larger than the delta H term. Okay? In your homework assignment tonight, you actually have numbers for this to make us kind of make more sense of it. Hopefully that made sense in that description there. I usually do this description for honors chemistry too, so it should hopefully make sense, but maybe as we do more of these, it will certainly sink in. An endothermic reaction. So once again, we have a positive delta H where the system decreases in entropy, so minus T times a negative delta S. Any value that you plug in for T for this, problem here is that this is going to be negative, right? Minus a negative, which means really plus a positive, which means that you have a positive plus a positive, which means there is no temperature that you can make this work. So a reaction that is both endothermic and decreases entropy doesn't even sound right. How would a reaction be absorbing energy and then also decreasing its entropy? That just doesn't even sound right, and so therefore it must not be right. And of course we can see here that there's no temperature that we can make this come out to be a negative value. Exothermic reaction, so now we have a negative delta H minus an increase in entropy, so that's positive. So you have a negative minus, or in other words, we could say a negative plus another negative value. Looks to me like there's always going to be a situation. So any temperature, this reaction will occur. And lastly, an exothermic reaction. So still delta H is negative, where the system decreases in entropy. This is also negative. So now it's like saying a negative plus a positive, then we need the delta H to be larger than the delta S term. So the only way we can control this, because we don't have control over the reaction, the only way we can control this is with temperature. So it looks like we want to have T be small. And I hope that all makes sense to you. But if it doesn't, do your homework assignment tonight, and then hopefully you'll see with the numbers that are given in the problem where you can make sense of it with temperatures. Okay? I do have answer slides for all, and I do even have some explanation stuff here too. So hopefully if you walk through this, you can maybe make sense of it where it looks cleaner. All right, question number 2. Now we do put some numbers into looking at how the process of melting of water is not spontaneous at -10, is spontaneous at +10. We know that. If you have a +10 degrees Celsius, ice is going to melt, and that it's equally favored at 0. Not flavored though, but favored. So we're using our Gibbs free energy equation. So, and actually they want us to do both. They want us to use both the Gibbs free energy equation and also look at delta S for the universe. Okay, so in the Gibbs free energy equation, we're going to say delta G equals, now it's endothermic, right? Absorbing energy in order to melt. So 60.3 kilojoules per mole. Let's just assume that there's 1 mole. Minus, okay, so -10 means 263 Kelvin. And then in order to be able to subtract these, the delta S has to be written in kilojoules per Kelvin. Remember, assuming 1 mole. So we're going to call this 0.0221 kilojoules per Kelvin. And then we're going to multiply and then subtract, and we get that one comes out to be +2 kilojoules. Now I didn't put any significant digits. You can get that from the next slide. I just wanted to show that it came out to be positive, which tells us that it's not spontaneous. Meanwhile, if we were to look at delta S for the universe, we could say that the delta S for the universe for this reaction would be equal to, beginning we would say delta S for the surroundings. Come on, pen. Plus delta S for the system. And the delta S for the surroundings, we have a substitution where we can put a negative delta H over T. I mean, really, by doing this, we're kind of already using Gibbs free energy equation is kind of intermingled into this already. And then delta S for the system is the 22.1. So we're going to say negative 60.3 kilojoules divided by the temperature of 263 Kelvin, then plus point, this is in kilojoules, so we still want to use 0.0221 kilojoules per Kelvin. See how they have the same units? Delta S for the universe comes out to be kilojoules per Kelvin, or we could have switched to joules per Kelvin, plug that into our calculator. There you can see it came out to be negative, and we know that delta S for the universe can't be negative. Okay? Now, I don't think I need to work this out for the other two for you, but you can look at this slide, and you should probably copy this down or at least walk through it so that you make sure you understand how this works. This is a crowd favorite on tests, is to solve this to show that something is spontaneous or not. But you can see here when we put in 283 for our temperature, positive 10 degrees Celsius, that now we get delta G is negative. When I do the same thing over here for delta S of the universe, I get a positive answer. And then when we put in 273, our point where ice is melting into liquid water, that it comes out to be a very, very small decimal for delta G. And based on rounding, why it's, we could round it to 0. And then delta S for the universe also comes out to be 0, so that we know that we're right on the verge of this changing states. Okay? Last question. At what temperatures is the following process spontaneous at 1 atmosphere? So 1 atmosphere just tells us that we can use the delta S that's there. Okay? To find the temperature, we need for delta G to be negative. So let's start by writing the equation since we haven't written this out. Well, I guess we did on the last slide. Negative T times delta S, such an important equation for us to use. It's so important that I'm even going to rewrite the delta G there to look prettier, because you have to be aware of this equation. Okay? This is the thing that tells us if a reaction is going to occur spontaneously or not, if it's thermodynamically favored. So what temperature means that we want this to come out to be negative. So I'm just going to put in a 0 for delta G, and then we'll consider how do we make this, when we solve for that T, whether we want to be above that or below that. So 31.0 kilojoules per mole. Once again, let's just assume 1 mole. So we can just say 31 kilojoules, and then minus T times 0.093 kilojoules per mole per Kelvin. Assuming 1 mole, we can kick out the moles there. Then we solve this equation to see what T comes out to be. And we get that T comes out to be 323.7 Kelvin. Okay, so now remember, we're trying to decide what temperature that this reaction is going to spontaneously, or this process is going to spontaneously occur, that the liquid bromine boils. So 323.7 Kelvin, if you plug that in here, we need this term to be larger than this term so that the delta G is negative. So that tells me I want to go to 323.8, right? 324 Kelvin is going to be my temperature where that occurs. What is the normal boiling point of bromine? I think if we were to Google search that, we're going to see that it's going to say 323.7 Kelvin. All right, because this Gibbs free energy equation is going to support what our boiling temperature is, because that's where the process becomes spontaneous. Chapter 16, homework number 2 is your assignment. A nice important one. Here's a couple questions to help us practice what we just did. So in number 7, looking and seeing with these particular numbers if it's spontaneous or not. Number 8, finding what temperature it starts to become spontaneous, and then some things like we just finished with there for 9 and 10. Very important assignment. Make sure you do it. All right, see you next time.